Hey everybody, thank you so much for joining us today for this installment of the SEAL Connect Classroom webinar. This is part two of a topic we touched on in our last webinar with a focus on packing. Today we're going to be discussing how to set up environmental controls and pump systems with a focus on mechanical seals. We're back with Chuck Tanner. He is the Director of Market Development for SEPCO. Here we go. So I just wanted to let y'all know, you can always follow us on social, where we're always posting content from SEAL Connect, which is our content library. You know, these webinars are an extension of that, where we hope to provide a lot of knowledge and resource to industry members, and just kind of be the place you go for all of your fluid sealing questions. You can also ask questions directly to Chuck or me in the questions section on the panel on the right, anytime during the webinar. If they're timely, I'll ask Chuck to pause as we address them. Otherwise, we'll talk about them at the end. We also have a copy of the PowerPoint that you can download. You'll also receive an email of that following this webinar. And this webinar is being recorded. So along with those slides, you're going to receive a link to the recording, and then later on it will be available on our YouTube channel. So again, so Chuck is going to be directing this webinar today. As I said, he's the Director of Market Development and has more than 30 years of experience in the pulp and paper industry, and he's been with SEPCO for 29 years. So Chuck, can you just give us a little background information on yourself and what sparked your interest in this industry, what led you here, and some of the exciting projects you're working on right now?
I started in this industry in 1984. And I had a really good mechanical background, and I'd been through a bunch of engineering school, and we ended up working for one of the competitors when I started in this business, and so I've been exposed to many different companies and many different products. I spent most of my tenure here at SEPCO, and a large portion of that tenure I have focused on the development of our pulp and paper in the pulp and paper industry and that market segment for SEPCO. That's just a huge market segment for these products, and we've been very successful in that endeavor. But
that's great.
What led me into this industry, just to be honest with you, it's kind of funny. I just kind of happened into it. I was a college graduate during the Carter administration, and jobs were real tough, and I gave this a try, and it stuck. And this is one of these industries that if you stick with it and then persevere through it, and it's unfortunately it's a lot of acquired knowledge. We didn't have these venues to share information when I started in this industry. And what's really nice about the SEAL Connect classrooms is we have this ability to share this information through this technology we have today, and it's not so much of a tribal knowledge anymore. We try to that's the focus of these webinars, is to try to share that knowledge where you don't have to go through the painful learning curves and the expensive learning curves as far as working in plants that they had to back in the early days of this industry. So
yeah, well, we surely appreciate you sharing your knowledge and your experience in these webinars. It's a great asset for anyone who's tuning in. So we're going to go ahead and get started now that we've kind of heard a little bit about Chuck and his background. Some of the topics we're going to touch on are, why stuffing box reliability is so important, what role mechanical seals play here, since we did discuss compression packing last time, and which environmental controls must be considered and how you can properly set them up. So Chuck, well, we're going to start with this poll. Sorry guys, I'm going to have to minimize my view really quick to launch this poll. But you should get that in just a minute. Yeah, so which of these is the most crucial environmental factor to monitor in a pump system? Heat, cooling, moisture, friction, or all the above? I'm going to give everyone just a second to select their answers. Yeah, so it looks like the majority of people chose heat. So Chuck, what do you have to say about that?
That's one of the key aspects that you have to monitor and to have a successful, reliable mechanical seal uh, program is heat is a killer for seals because we're going to talk about some of the aspects with some of the things that heat does to you when dealing with mechanical seals and through the presentation, and you'll have a clear understanding of the problems that those factors cause.
Great. Awesome, Chuck. I'm going to let you take over. If you need to change the slide, just prompt me,
Okay.
and we're good to go. Take it away.
Thanks, Anna Claire. Well, thanks everybody for joining us today. This is this discussion today is one of the most critical things and critical pieces of knowledge you can have to have a really good, reliable mechanical seal program. We're going to cover a lot of topics today on how to set your seals up, what's the most reliable solutions to handling all these adverse operational conditions. There's two things that you have to understand about a mechanical seal. There's two ways to come to a solution and design a solution for your mechanical sealing issues. One is you can design a seal specifically for sealing a particular application. That's common in boiler feed water applications and things like that you have mechanical characteristics when the piece of equipment that you have to design into the seal. You have, cooling considerations that you have to design into the seal. But when you get into really special applications like that, the only true solution to solving mechanical seal issues in those critical applications is to design a seal that will run in those operating parameters and design for all the mechanical issues that you can have with the piece of equipment you're trying to seal, mixers and all that sort of thing. They all have to have seals specially designed for them. The other option, which is the most cost-effective option that most people do today, is they buy off-the-shelf standard seals and to fit ANSI equipment, and that is the most cost-effective way to solve those problems. But those solutions come with some limitations. I mean, you're talking about in the first option, you're talking about seals that cost thousands of dollars instead of hundreds of dollars, and so you kind of have to make a trade-off when you take the second choice and pick seals that are off the shelf, but you may have to do things to the seal to try to create a good operational environment for the seal so the seal will run in its design operating condition. You can't do things with off the shelf box seals, standard seals that they're not designed to do. And some of these discussions we're going to have today is how to set up the proper cooling, cleaning environment for that seal to get the maximum reliable performance out of it. Okay, Anna Claire, you just change the slide if you would. The things that environmental controls do to seals, it's not just about protecting the environment. We're not talking about just protecting the environment from hazards. We're talking about creating an environment for the seal to run in its most designed state. Of course, the reason we run mechanical seals, is improve environmental protection. There's products that we see in industry today that we don't want to get out into the environment that are hazardous to health and hazardous to wildlife and hazardous to our water system. So we don't want those things to get out. A lot of products today are PSM products. They're product safety products, and so things that we pump today. A lot of those things fall under PSM regulations, and we have to protect the environment, protect human life from those products. Things like chlorine dioxide in the paper industry and that sort of thing. We can't let those products our employees get exposed to those products, and the environment get exposed to products. The other thing becomes financial issues. Protect to
apply the correct environmental controls to create the correct environment for the seal to run in, not just the external environment. We're talking about the internal environment for the seal to run in, is improve process efficiency. We're talking about reducing product contamination from the fluids that you use to create the environment for the seal to run in. And we're talking about one of the things that people forget is we're also talking about, when we talk about improving efficiency, we're talking about improving equipment availability to production. That's a cost and downtime is a cost that we have to consider when we look at providing and creating the correct environment for the seal to run in. So again, we're talking about external environment, personnel safety, employee safety, housekeeping issues, and environmental impact on the world we live in. But now we're also talking about the internal environment that seal has to live in to survive. And also creating that environment and that proper environment for the seal to live and to operate and be efficient and get good longevity out of it reduces replacement cost, material and labor cost to replace that seal. Most people, when they change a mechanical seal, they change a whole rotating assembly for a pump or the piece of equipment. They have new bearings, they start all over again. So it's not just the cost of the seal involved in it, it's the cost of the actual piece of rotating equipment that you have to take in consideration when you do that. When you look at the total cost of a standard ANSI pump replacement, I've looked at some of these numbers from Goulds and different manufacturers. The loss availability of that equipment, the downtime cost, and the replacement cost that goes with that piece of equipment is upwards of a standard small mid-frame ANSI pump is upwards of about $20,000-$25,000 per replacement. So a $1,500, $2,000 mechanical seal, those premature failures, but not operating within their design criteria, become very expensive very quickly, because it's the seal itself is only 15-20% of the cost of that repair. The real cost of that repair is those other lost opportunities and those other costs. So things that we're going to talk about in setting up a proper environment for the seal to get lubrication, to eliminate corrosion and erosion of the components of the seal. Seal components are very, very thin. We fit in a very limited cross section and a very limited space in most standard ANSI stuffing boxes. So by those design limitations, we make components that are very, very thin walled, that are subject to changes in fluid temperature from expansion and contraction. In other words, if you've got carbon holders and holders that are holding faces, when you put them under extreme temperatures, we have to take in consideration expansion and contraction of the holders that we press the components in. Pressures. Most seals, most standard seals are designed, off-the-shelf seals designed for up to 150 psi stuffing box pressure. In reality, in most cases, if you get over 100 psi stuffing box pressure, you need to consult with the manufacturer of those seals to make sure that you don't have any distortion of the face materials, because those two faces are precision lapped. They're within like 23 millionths of an inch. So those things have to keep their flatness to control the molecules of the product that you're running across them to lubricate. So you need to make sure that the seal that you're using can handle the pressure limit, the pressures that you're going to put them under. Another problem you get into with some pumping applications on ANSI pumps is face lubrication and boundary lubrication. You may not have enough pressure in the seal chamber of the stuffing box to force lubrication across the faces to effectively lubricate the seal, because the seal is using either some product that you inject to the seal to lubricate between those faces, or it's using some external fluid
to lubricate those faces. So you've got to have lubrication between the two faces, and the two faces where they don't run dry. And so boundary lubrication and having enough seal chamber pressure is really important. If not, we're going to talk about how you can create that kind of pressure to where you get proper face lubrication. And the fluid properties. What happens to the fluid if you're going to use it, whatever you're using for lubricant, whether it's the product you're pumping or some external lubricant? What happens to that lubricant that you're using when it heats? You got to remember that you got two faces running together that generate heat. What happens to those products when you run it across that face? Glues and adhesives and those sort of things, they may be a liquid state when you're pumping it, but as it runs across that face, it could polymerize. In other words, when you take it and it will ball up and roll up, and basically you're generating heat between the faces, and you're curing the product from the heat you're generating between the faces. So those type asphalt, those sort of things are abrasive, and paints that have abrasive materials in them, those materials will not lubricate a face, and they'll actually dry between the faces as they're running, and it makes like little balls when it rolls. It polymerizes. Another one that's real common in industry is hot water. Water over 170 degrees, 160 degrees, you have to take special consideration with water, because water, even though at lower temperatures is a perfectly acceptable face lubricant, at elevated temperatures, water, as it moves across the seal face and you get a pressure drop across the seal face. Understand, no seal is 100% leak free. Seals leak vapors. And what you're doing is you're getting a pressure drop across that face to the atmospheric side, and the product you're pumping will go to a vapor. That's the reason we have double seals and single seals. Some products you have to catch those vapors, but you have to water, as you're creating that additional heat between the faces. Everybody knows water, when it goes back, you heat it up, it goes back to steam. Well, steam expands. You can put mechanical seals in hot water, and over time, the seals will fail over time. In the beginning, they'll run fine, but over time, they'll fail. And what's happening is the water goes to steam, and you get these little explosions between the faces, and it chips the faces away. So the most common thing that's sealed in industry is hot water. That's one of the most common things, and you have to take special consideration when you seal hot water, with heat exchangers and different things that you do to help cool that water down, because hot water is a poor lubricant. Okay, Anna Claire. Things that you have to consider when you're dealing with temperatures. And elastomers is a big thing. Most seal companies will use Aflas or Viton or EPR. If you get to some of these elevated temperatures, you're stuck with using some of these higher temperature elastomers like Calres and those things. And this market today with Calres, those of you that are using Calres, you need to be very careful about your Calres inventories these days, because a lot of that material that's used to make those elastomers comes from Russia, and as we know today, that we can't get those materials. So if you know that you have applications that you require Calres, please make sure that you have adequate inventory, maybe a couple of years worth of inventory in the future, because it's getting a little bit difficult to get those things. And we maybe have to resort back to using graphite wedges and those sort of things in higher temperature applications because of availability of elastomers. Distortion of components because of high heat. You've got face materials that are pressed in metal holders that have different rates of expansion, and you can end up with distortion of seal faces and loss of flatness because of higher temperatures. And some fluids change viscosity at higher temperatures, and and reduce the ability to lubricate a seal face. So things that are low temperature may lubricate, but when you get to an elevated temperature, not only from the process, but from the heat generated between the faces, can lose the lubricating properties. And excessive fluid flashing, like we talked about with water. Some hydrocarbons do that. They'll flash at elevated temperatures, and they will not lubricate seal faces and cause the faces to run dry. And another thing that in acids and those sorts of things, at higher temperatures, you get acceleration of corrosion of metal parts. So you may have to use upgraded metal parts in your seals to handle corrosive environments, excessive corrosive environments because of acceleration. And another thing that people need to consider when you spec a seal is cleaning procedures. A lot of plants have clean out procedures that they go through that's not typically what the seal is designed to see, that you have to take in consideration some of those cleaning procedures and when you make a recommendation. Let's talk about pressures. Pressures can, like we talked about before, can cause your seal faces to distort. Most seals are balanced up to, off-the-shelf seals are balanced up to 150 psi. But again, I would recommend anything over 100 psi stuffing box pressure. You consult with your seal manufacturer to make sure that there's not anything that we need to do with those applications, and changing balance ratios to lighten the load on the faces and things that can give you better reliability. Those pressures in unbalanced seals can cause excessive closings of the face and excessive face loading, which adds more load between the faces, adds more friction, more heat, and restricts the lubrication of the faces. Any of these pressures they'll actually, it's kind of like, I kind of equate it to if you rode down the road with all the time with your truck and you had a load of sand, you were riding in the back of your truck and you couldn't understand why your tires are wearing out. That's what seal balancing does. It lightens the load on those faces to keep the loading to a minimum, even at elevated pressures. And we talked about flashing of products between the faces and some of the earlier part of this discussion, like water and hydrocarbons and hot water and hydrocarbons, those things. If you're going to run anything that the face heat generation is going to get close to the boiling point, all of these environmental controls are important to create that environment for that seal to fight all of these design limitations within the seal. So, talk about fluid properties. Things. Understand you're trying to lubricate two faces. So when you make a decision about what to do and how to set up environmental controls on a seal, you need to decide whether the product you're pumping will actually lubricate a face and not cause you any harm to the seal. Things that you want to consider is fine particles in the fluid that can be carried between the faces, fiber material, things that has suspended materials that you're pumping has suspended fibers in it. Those fibers, not only can they get into the seal, but they can actually get into the stuffing box cavity and they'll dewater. And when they get in there, in the dewater, and get trapped in those around the seal, those fibers can actually damage the seal and cut the metal parts and abrade the metal parts away. And if you're flushing or using one of the discharge bypasses or things like that to create the environment for the seal to run in, some of those products that you're pumping, like sand and things like that, can be abrasive, and you're running that back into the seal chamber at higher pressures can be abrasive to the metal parts.
And some fluids can change state. Some can solidify with temperature changes. They can polymerize, like we have talked before, and cause heat and shear. Some chemicals can crystallize between the faces. Paints and glues, well, they'll harden when exposed to the atmosphere. Hydrocarbons will coke. In other words, what will happen is, we talked about the seal leaking vapors to the atmosphere. Things like vegetable fiber and hydrocarbons and things like that can coke on the atmospheric side of the seal and actually cause spring clogging and things like that from the atmospheric side of the seal. And some products will flash to a gas when you generate seal face heat between the faces. And all hazardous, toxic, explosive, corrosive materials really need to be contained with some sort of secondary seal. Most things like that are hazardous are double seal applications. So you pick the right seal for the right place based on your environmental control, availability, or limitations that you have. So if you've got places where you can have access to, there's two things you need to remember about a mechanical seal. You keep it cool, keep it clean, you'll get good service out of it. If you don't do that, you will not get good service. So when you're making a recommendation, this kind of falls into the recommendation portion a little bit, because when you make a recommendation, you got to determine how you're going to create an environment for that seal to run and where you're going to get the source to create that environment. To make a decision, you make make a choice on the correct seal, whether you're going to run a double or a single, and how are you going to protect the seal to make it have good reliability. So that's what you've got to do up to this point. So we're fixing to talk about how to do that with single seals. This is we're going to talk about these flush plans for mechanical seals. This is two common flush plans you see with a single seal, where you flush with an external source. Some just to give you kind of broad spectrum of some of the options that you've got. When you flush from an external source, you may have to run that external source straight. You may have to run it through a cooler to cool the fluid down. You're injecting in there. Remember, what we're trying to do, the objective is to create the proper running environment to meet the design criteria and the limitations of the seal. And all seals have those limitations. There's even the special design mechanical seals, they can design things that handle higher pressures and equipment movement and that sort of thing. But the basic face lubrication principles, whether it's a custom seal or an off-the-shelf, out-of-the-box standard ANSI seal, the face lubrication is what we're going to be talking about in the next few minutes. And that's what's critical, to have enough pressure to lubricate the face and have something cool and clean to lubricate the face. You can go ahead and a clearance change. API plan 11. This is a very common plan that's used by the pump companies, and what it is, it's a bypass flush from the discharge of the pump into the gland of the seal to keep the environment around the seal, keep the solids and keep it cool out and keep it cool and keep it clean and keep fluid moving through the stuffing box. Stuffing boxes and seal chambers have a tendency to want to hold fluid, and the fluid kind of deadheads in there. And what you're trying to do is try to get that fluid flow from out of that stuffing box or seal chamber back into the pumpage and keep something cooler running through there. If you had a water pump, for instance, and you ran it without a discharge bypass, the water that's around the seal face that's in the back of that stuffing box is going to kind of be stagnant, and it's not wanting to flow through there and keep a cleaner, cooler fluid around it. And you're just kind of trapping the fluid in there, and you want that fluid to flow or from around that seal face back into the pumpage and keep something cooler in there all the time, instead of trapping fluid back there. A bypass like this is really recommended only in clean products. You don't really want to put this in any slurries because the orifices in the seals are small. If you run slurries through there, you'll plug the orifices up. You don't really want to run anything this API 11 plan in any applications that the product is not fairly clean. You know, this plan will keep products from becoming stagnant around the seal faces and causing heat buildup and flashing of products and that sort of thing. That's typically what you use this for. And if you buy a pump from the pump company, a lot of them will come in and they'll already have them set up like this. This API Plan 11 is very common. But you got to decide, even if you buy a pump that the pump company spec, based on the product that you're pumping and what you're using to lubricate the seal face, is that the right lubricant? Is that product you're pumping the right lubricant to lubricate that face? The Plan 11 just creates the effect of circulation to keep that area around the seal with a cool product around it. Okay, I'm clear. Suction bypass. You know, suction bypass is used in a lot of applications where you have high stuffing box pressures, or applications where operations may deadhead a pump and cause stuffing box pressures to elevate. If you go back, run a line from the gland back to suction, what that does is that reduces the pressure in the stuffing box closer to suction pressure and tries to maintain that pressure at suction pressure. And it also aids in circulation. The only problem you get into is in ANSI pumps. A lot of ANSI pumps, the stuffing box pressure is very, very close to suction pressure. And so the circulation through this Plan 13 is not as good as Plan 11. So it has its uses, and especially places where you have very high stuffing box pressure. But again, this is used in applications that the product you're pumping is fairly clean. So remember, this is a single seal application, and you're using your pumpage as a lubricant. API Plan 14. This is a combination of a discharge bypass and a suction bypass. And what this is typically used for is in ANSI pumps where you have slurries that will lubricate a seal face. So what you do is you put your discharge bypass line into the flush port of the stuffing box or the seal chamber. Because if you've got a slurry, you do not want to inject that slurry on top of the seal and worry about abrading the seal itself. Then you run a line from the seal gland itself back to suction. And what this will do, this will elevate the pressures in the stuffing box, and it will allow you to pull those fluids back from that stuffing box back to the suction side of the pump to create circulation. Now, the only caveat to these applications is sometimes where you've got oversized stuffing boxes, it'll reduce the effectiveness of this because the orifice sizes in the stuffing boxes in the glands are smaller, so small they're too small to handle the volume that you have in an oversized stuffing box to get it to actually circulate well. So, but this is a common used. This Plan 14 is very commonly used but it's used mostly where you have slurries that will actually lubricate the seal faces. Remember, this whole discussion is about having and setting up a proper environment that will meet the design criteria for the seal. That's what we're trying to do. We're trying to create the place where you'll get the maximum reliability of the seal and maximum coolness, keeping the seal cool and keeping it as clean as you can. That's what this whole discussion is about. This is the heart and the soul of having good mechanical seal reliability. Everybody's mechanical seal uses the same technology, the same face technology. There's no difference in anybody's components. It's the fact of the way you set it up to get good results out of that, the application of the products. So that's going to just about, well, we got the external flush. And the API Plan 32 uses an external flush from a clean source. So in other words, if you're pumping a product that's a dirty slurry, we're going to use clean plant water or some other external source that's compatible with the product that you're pumping. And we're going to create an environment around that seal to where that seal is running in the fluid that you're flushing with and not the fluid that the pump is pumping. A lot of people in the bottom of the stuffing box in these type applications will put a restriction bushing in the bottom of the stuffing box to restrict the flow back into the stuffing box. It's a close fit bushing, so we're actually closing the seal chamber up to keep things from going back in that stuffing box because we're flushing at a higher pressure than what the process pressure is trying to go back into that box. And what we're doing is the seal is got an environment that's very similar to the product that you're injecting in there when you do that. This Plan 32 is a very inexpensive way to run mechanical seals in slurries where you don't really want to run a double seal and go to the expense of running a double seal. Because in slurries, you got two choices. You run a double seal and put barrier fluids on the double seal, or you can run a single seal and use a flush and restrict the flow of the slurry back into the box. So that's your two options. But Plan 32 from external flush source is very common. And of course, the fluid that you're pumping, that you're putting in there is going to go in the process. So you're going to get product dilution and all that sort of thing when you make this choice. But from a cost-effective standpoint, a lot of people versus double seals will opt for a Plan 32.
Hey guys, I'm gonna minimize my screen again to launch this poll. And I apologize if you hear my dogs barking in the backyard. I was lucky I got them out of the house. Okay, so what is the importance, if any of you attended last month's webinar, these are the same that we had then, but we're interested to know, with those of you who are interested in this one with the focus on mechanical seals, what is the importance of water consumption at your facility on a scale of 1 to 5, 1 being the least important, 5 being the most important? So I'm going to give everyone just a couple minutes to answer. You can select one of these as multiple choice. I'm going to go ahead and close it out. So it looks like everyone was kind of right in the middle, right at 3. And Chuck, you can take it.
Okay. You can go ahead, Sarah, but Anna Claire, excuse me. Let's talk about double seal environmental controls. A double seal is nothing more than 2 mechanical seals, and you're injecting your barrier fluid or your flushing fluid. For those of you that don't know what barrier fluid, when we refer to barrier fluid mechanical sealing, it's nothing more than the flushing fluid that you just like you talk about a single seal or packing. They just happen to call this fluid a barrier fluid. But you got to understand something about double seals before we have this discussion at all. There's 2 ways that you can operate a double seal. Most people's double seals are double balanced. That means they seal in both directions. There's two ways to run a double seal. You can operate it in a double mode or a tandem operational mode. The only difference between those two modes of operation is the pressure that you put between the two seals. You understand, you got two seals that are back to back, and you're injecting your barrier fluid or your flushing fluid in between the two seals. And the only difference is the pressures that you inject between the two seals. It's very important you understand this concept moving forward. Double seals, we inject the fluid between the two seals inside the seal cavity itself, not the pump stuffing box, but the seal cavity itself at a higher pressure at 15 to 20 psi above the maximum stuffing box pressure, so that we can be assured that the seal will run in double mode. When I say maximum stuffing box pressure, it's really important that you put gauges in the flush ports or the seal chambers of the stuffing box you're operating in, so you'll know exactly what that stuffing box pressure is. So what happens is when you eject that barrier fluid between those two seals at 15 to 20 psi above that maximum stuffing box pressure, also make sure that when we talk about maximum stuffing box pressure, if operations deadheads that pump, we need that fluid injected at that increased elevated pressure, the maximum pressure that seal is going to see in operations. So you've got operations out there where they deadhead a pump. When you deadhead that pump, that stuffing box or seal chamber pressure is going to be elevated. So we need to make sure that that fluid that you're putting in between those two seals is 15 to 20 psi above that maximum pressure. Also, cleaning operations. If you steam the pump or whatever you do to the pump, you got to make sure that that seal, that barrier fluid, is at a higher pressure than the pressure you're going to put in there to clean with. Now, if you'll limit your cleaning procedures, if you use steam, 100 pounds steam, 150 pounds steam, whatever, if they'll steam it and don't run the pump, you'll be okay, and don't worry about that elevated pressure. But if they steam it and run that pump, you have got to have enough barrier fluid pressure in between those two seals to overcome that steam pressure. Because if you don't, the inboard seal will fail because it ends up on steam, because the pressure, higher pressure goes to lower pressure. So the inboard seal will end up on steam. You'll end up with premature seal failure. So be very careful about that. Tandem sealing is something totally different. When we talk about tandem sealing, we're talking about running the seal with the barrier fluid pressure at a lower pressure than what the seal chamber or stuffing box pressure is. Tandem seals are used, but you got to have enough pressure there with a tandem seal to have good boundary lubrication on your very outboard seal. So can you run 5 pounds of water in there, 10 pounds of water in there? You need to run enough pressure through that seal when you're flushing it or running your barrier fluid to actually lubricate the outboard seal. I mean, if you run 2 pounds of air differential, 2 pounds of pressure in there, that may not be enough to lubricate that face. I would consult with the manufacturer of the seal to make sure that you get good boundary lubrication, so you don't end up with an outboard seal failure simply because you don't have enough internal pressure in the seal to make the seal run properly. So that's the only caution about running seals tandem, is make sure you're putting enough pressure in there to get good lubrication for the outside face. So everybody understands you got double operational mode where you got a higher pressure of barrier fluid than the process pressure that's trying to overcome it. Tandem mode, you use a lower pressure than the operational pressure the seal's operating in. So as long as you understand those two concepts moving forward, all the rest of this will not be Greek. You'll have a clear understanding of what we're talking about. Typical double seal Plan 54 operations, and this is used very commonly in a lot of industries. This is where you actually
run the seal as a double seal. Most people plumb it up to some plant source of lubrication. It could be that. Some people have an oil system. The industry I'm familiar with uses water, and they run water through the seals at a higher pressure than what the process pressure is to lubricate the outboard face and the inboard face with the product you're running. This is typically done in slurry applications and products that are sticky, that's not going to lubricate, glues, adhesives, all that sort of stuff. Anything that's compatible with the fluid that you're running through this seal. So if you get an inboard seal leak or an inboard seal failure, you do not contaminate a batch of product. So you got to make double sure you can't, if it's water, if it's a glue or an adhesive, if the customer can tolerate dilution of that product, if it's a water-based glue adhesive and he don't really care, you can do that. But that's one of the things you need to make clear with the customer, that product has an opportunity to leak in there. The other thing is when you plumb a seal up with Plan 54, always use a stuffing box gauge where you know what the stuffing box pressure is. Use a valve going into the seal, a gauge coming out of the seal, and a gauge to throttle the pressure back on the outboard side of the seal. Now, what we're talking about doing is we're not talking about using lots and lots of barrier fluid. We want a very low flow through it. We're talking about pressures. We want you to maintain that pressure 15 to 20 psi above what that maximum stuffing box or seal chamber can be. So it's very simple. This is probably the most common way double seals are set up, and they're all set up that way. Moving forward, we're just going to talk about instead of using some external plant source of fluid, we're going to talk about using contained fluid and use different methods to circulate the fluid through the seals. But this is the basic concept of the way a double seal works, the way you plumb it up. Always plumb into the bottom port and plumb out the top port. That way you make sure you don't have any air entrapment within the seal. If you plumb in the top and at the bottom, you could end up with some air entrapment in the top of the seal. Make sure the seal is totally flooded, and make sure the seal has got fluid completely encasing the seal to make sure you get good lubrication. All right, Hannah Claire. Now, API Plan 53A is where we use a convection tank or a barrier fluid tank to seal the seal. Same concept, okay? What we're doing is we have a tank that's contained. If you have an application where you cannot have or don't have an external source of fluid to lubricate the seal, you can use, water glycol, different kind of oils, some solvents. You need to be very careful if you use solvents, because they have a very low flash point. So you need to consult with your sealing supplier to make sure you can do that. But what we're doing, we're putting a fluid in a tank. We're pressurizing that with some plant system, most of the time with air and nitrogen. That air and nitrogen pad on that tank keeps that fluid pressure 15 to 20 psi above what that stuffing box pressure is. And this system's a little unique. It works on convection. So basically, when you heat a fluid up, the fluid changes density, it becomes lighter, and the fluid will rise, just kind of like air. And what you're doing is you're running that fluid into the bottom of that seal. It's heated up within that seal by the process, and as it heats up on the discharge line, it rises on its own back to the tank. One thing you have to be aware of when you do this is how many BTUs you generate. A typical tank will displace 300 300 BTUs. If you have over 300 BTUs generated, you have to use cooling coils in the tank and cool the fluid you have in the tank to get it to circulate properly. Because what can happen is the BTUs can accumulate in the tank, and you get the tank up to its maximum BTU capacity, and the thing will cease to circulate. So always, if you think you're generating too many BTUs and heat within the seal and the process on the discharge side, always use a tank that's got coils in it and cool them, and cool the fluid in the tank down to get it to circulate correctly. And placement of the tank. The tank needs to be placed in the vicinity of the center line of the shaft. All manufacturers will tell you and give you drawings and tell you exactly how far to put the tank from the center line of the shaft and the elevation of the tank and all that, because if you put the tank too far away, the fluid will cool in the line going back to the tank and not in the tank, and the tank will not cease to circulate, and you end up with excessive heat generated to seal faces, and the seal will not the fluid will not circulate through the seal. A lot of seal companies use pumping rings and that sort of thing to aid in the movement of the fluid. If you're going to operate one of these systems, I would probably strongly suggest that you use a seal with a pumping ring in it. That aids in that circulation. It doesn't rely totally on heating and convection to get the fluid to circulate. But be very careful about the BTUs generated to make sure you maintain that convection through the system. Plan 52, we talked about running seals in tandem. Plan 52 is the arrangement that you use to run tandem seals with a barrier fluid pressure is less than what the pump process pressure is. And what that does, that keeps emissions and vapor. We talked about seals leaking vapors. This is places where you want to contain vapors, maybe the vapors that the seal emit, or maybe a environmental hazard, and you want to contain those vapors, or you have a fluid that you're pumping that may be very hazardous, that in essence what you're doing is you're running the outside seal as a insurance to make sure you do not uh, expose the environment some of these hazardous materials. One thing about this setup and this API Plan 11, you got to make sure that the inboard seal is got enough pressure on it in the stuffing box to have good boundary lubrication, have good lubrication. So if you don't, you can make one thing you can do, you can take combinations of single seal environmental controls and add them with double seal environmental controls. You may run discharge bypasses where you can elevate the stuffing box pressure for the inboard seal in these applications like this, where you get good lubrication of the inboard seal. There's all sorts of things you can do and things you can combine to get better seal life. You're not limited just because you're going to run one of these API plans. You're not limited to doing other things with it and combining other things with these different plans. You can have an API plan 11 and an API plan 52 and run both of them. So there's situations where, especially with this plan 52, where you're basically running your inboard seal as a single seal and your outboard seal is a single seal, sealing different products because you run the seal in tandem. But you got to also make sure that inboard seal is getting proper lubrication in the process. So there's things that you can do with this, and things that your seal manufacturer will recommend you do with this based on the lubricating pressures and things that's available for that inboard seal. So when in doubt, call your supplier and discuss it with them, and they may recommend that you put a Plan 11 with this. But the Plan 52 is basically set up for mostly hazardous chemicals and processes that they can't allow even any vapors to escape in the atmosphere. Final thoughts. As we've discussed during this podcast, environmental controls are crucial to get maximum seal life. You got to run the seals within the design criteria and the limitations that you have. The environmental controls remove heat. The environmental controls will provide proper lubrication for the seals. The environmental controls provide a clean environment for the seal to operate. If you just kind of keep in mind that you're lubricating faces and that your main criteria is to provide a cool, clean environment for those faces to run, and that should be your first and foremost thought when designing and picking seal faces and picking what lubricants to use on the faces, whether it's your processed fluids or there's some external source of fluids. How can I keep that set of faces running in the coolest, cleanest environment I can to get the maximum seal life? And
awesome. Thank you so much, Chuck. This was such a great presentation, and just we really appreciate your expertise and all of your advice and thoughts on this. For everyone who is watching this live or watching the recording, please feel free to reach out to Chuck directly. You can email or call him with your questions, or if you want to talk about any of our sealing solutions, he'd be happy to talk with you about that. Thank you so much to everyone who tuned in today. We really appreciate it. Again, you're going to be contacted with an email following this live event with a link to a live recording, to the recording, and also to a file with the slides. And just stay tuned. We have more exciting topics coming up in the Seal Connect Classroom series. And you can always check out our Seal Connect website for more exciting content in all areas of fluid sealing. Chuck, thank you so much. Really appreciate your time today and all of the work you put in getting this presentation ready.
Thanks everybody for attending today. We really appreciate your time.
Yep, thank you so much, and we hope that you all have a wonderful day.
We out?
Yes.